Hello, and welcome to the Engineering Dynamics Course Companion, Class 5. This is our last class in kinematics of particles. In the next class, we'll deal with kinetics of particles. This is the second of the non-rectangular coordinate systems classes. In the last class, we dealt with path coordinates, aka tangential and normal coordinates, and now we're going to deal with polar coordinates. Something I should mention in every class, if you go to the description below, you'll see that there's a table of contents for this video, and you can click on the links and you could jump to the example if you don't want to cover the bottom line up front or the condensed lecture portion. So the bottom line up front for polar coordinates, which we can also be called radial and transverse, we're rotating about an origin and we follow the particle. As opposed to the path coordinates where the coordinate system followed the particle, right, was along for the ride with the particle. Now we're like fixed to some point, and that's going to be like the reference point that we make while we're watching the particle, right? And we use the distance from that origin, that reference point, and we also use so we have the distance from that, and we also have the angle from some reference, which is usually the horizontal when we're dealing with two dimensions. In this case, velocity is now expressed in terms of the rate of change of the distance from the origin, right? So that's going to be a magnitude r dot with a unit vector er for radial. And then we have the magnitude of the other coordinate component of the velocity is going to be r theta dot. And that's going to be in the e theta unit vector right there. So that's r theta dot, right? So, theta dot is going to be this rotation of the thing, right? So there's theta dot, and here's r. So there's going to be a component of velocity that's going to be that r times theta dot. That's right there, right? And then the other one is going to be r dot right here. So we're going to cover that again some more. But that's how that's expressed. Now, acceleration has a whole bunch of extra terms, which is a little bit annoying, but it's important that we get used to this. So there's a little more. This is probably one of the more the aspect that students struggle the most with. So let's make sure that we get very clear on what's going on here. We still have these two unit vectors in the r direction and the e theta direction. But we have four different components. I call them variables of interest. No, that's not. Actually, there's more than four variables. But there's four things that we want to concentrate on, two for each component. One is r double dot, right? So that's like, just like there was r dot, there's the r double dot is the acceleration of the length changing of that distance from the reference. We have this r theta double dot, r times theta dot squared, right? And we'll see later, we can prove to you that that's a lot like, and in fact identical to, the acceleration we got in the normal direction in path coordinates. And we'll see, even though we had v squared over, remember, that was the acceleration in the normal direction right here. Well, we will see that we can, it's actually identical. We've just moved some things around, right? We've just replaced this for that velocity. And then we'll see, okay. And then we have r theta double dot, right? So that's really similar to this, right? That's the, so theta double dot would be like coming in right here, so that would be that aspect of the component. And then this last one, this is sort of this extra crazy guy, and this one is a combination, and we'll see. Hopefully, I've included it. We'll see how that fell out, and it's actually got its own name, and maybe you've heard of it before, relating to toilets. and the direction that they drain, depending on the southern hemisphere and the northern hemisphere. It's not true, by the way. But anyway, that's Coriolis acceleration, that r dot and that theta dot. It's got a 2 in there as well. So that's the bottom line up front. Here's all the stuff that we want to try to cover. We can't learn it all just by seeing it. Let's look into it in a little bit more depth. Right? So you'll recall here's the visual mnemonic from the last class, and I mentioned that we're going to have polar coordinates, aka radial and transverse, and we're going to use that kind of idea, right? So here's the same or a similar curve that we experience in path coordinates, but now you can see that the coordinate, the unit vectors right here, are not aligned with the path, but they're aligned with this point 0, right? This origin, where ER points outwards towards, away from the origin towards the point, and keeps going. And remember, unit vectors have a length of 1, right? And they don't, by the way, the unit vector doesn't have to be attached to that point. This is just for illustration. It could be floating anywhere along there, but it's nice to have it right here. And we define quite often, we really like to define always, if we can, use counterclockwise as being the positive direction for theta. We might run into instances where we can, momentarily for a particular situation, go ahead and, because we could actually, if we wanted to, we could pretend that this was written on a piece of glass, and we could rock around to the opposite side of the glass, and therefore theta would now be clockwise, right? But let's not go crazy there. But anyway, that kind of determines which direction this E theta is going to be, right? It's going to be, because we choose the thing to be counterclockwise, we point it over to the left of the thing. Now, we see here, if we put, you can see the velocity here is still tangent to the path, right? But now the components, it has components in the r direction and in the theta direction. In this case, it's a negative theta direction, you'll notice, right? And we also have components of the acceleration, which has, some of it is going to be towards the center of the curvature. So here you go. Here is the equations that we've already presented for you, and when noticing the various elements of them in the part. So when setting this up, I think a good attack, a good way to think of these problems is something I refer to as the VOI, the variables of interest, right? You'll see that there's an R's and there's R dots and R double dots and thetas and theta dot and theta double. Let's say, well, there's really going to be like 6 of these variables of interest, right? And so maybe in the problem you were given all of these, or maybe you were given some and then you were given some other information and you'd have to find these, right? But by concentrating on these and using these as the important thing to look for, you'll be able to organize your problem better, right? To be able to look for the variables of interest, right? So here's a quick and dirty derivation about where the acceleration components come from, or even I think where the velocity components right here, right? So the R, the position vector is actually, doesn't really need the E theta in it, okay? Because ER is defined, its angle is defined, right? The unit vector is already defined, this ER right here. So all you really need is a magnitude and the ER to be able to get it. But it's when you take the derivative of it, and remember, we think a couple classes ago, maybe it was in class 3, we're in class 5 now. In class 3, you want to go back and take a look. We went through and did the derivation of vectors, and we saw that there was the product rule that we had to deal with, right? And so because of the product rule, we also have to take the derivative of the unit vector, right? So we took the derivative of the magnitude, which is r, but we also had to take the derivative of er. And when we do that, we could set up and we could see what happens here, right? So if we have 2 different points, and I decided to go a new curve, and this curve is deciding to go up and to the left. That's so that like my E theta is actually positive here. And if we take a look at so here's the new ER prime, right? At the new point. If we take a look at that ER and that ER prime, we note that the difference, the delta, is going to be pointed in that way. Now, already that's getting, this depends on the sweep of the angle that we're taking when we're moving from one point to another. But we already can see that delta ER is looking like it's pointing in the E theta direction, right? And so as we take the limit, right, as that theta, that delta theta that we have gets smaller and smaller, we see that it does become E theta, right? And now we can use the chain rule, right? And because we don't, this is with respect to theta, but we want to do it with respect to time, right? Here's the thing we want to turn this into. And what we find here, right, is that we can use the chain rule, right? These two right here will cancel out, right, if we multiply those by there. But we also know that d theta dt can be defined as theta dot. So we can replace that in there and say that when you take the derivative of ER, what you get is theta dot E theta, right? So just replace that in there. And that's how we get this velocity. Now, if you do the same thing, okay, I need to erase this up here. If you do a similar thing that we did to this guy, do them now to this, and I guess we're jumping ahead, but we'll go ahead and do it. We'll take an E, what happens to this guy when we move from E theta to E theta prime, right? Well, we're going to be looking at our delta E theta right here, and we could see that even from right here, just take a look. You could see that it's pointing, I'm getting too much purple in there, right? We could see that it's pointing in that direction, which is in the negative ER direction, right? It's pointing towards there. So that we could see that's the consequence of that. But once again, that's d theta. If instead we want to do it with respect to time, what we have to do is do the chain rule again by multiplying it by d theta dt, which is theta dot, right? So what we get is negative theta dot ER. That's so let's go back and we'll jump back to what happens when we take the derivative of that velocity that we just got. We just got this velocity. Now we want to get the acceleration. So what we do is we do the chain rule again, right? The product rule, excuse me. So ER is R dot becomes R double dot. ER, now because we're taking the time derivative of it, becomes theta dot E theta. That's this guy right here, right? Remember? And then let's see. Okay, so now we have to do that. Now we have three parts to this guy right here, right? We have R, we have theta dot, and we have E theta. So we'll go and do the product rule at one at a time. So we have R, so we have R double dot, excuse me, R dot. We have theta dot, so now we have theta double dot. And then lastly, we have E theta, which we have to dot. And we know from over here, that's going to be negative right here. So if we gather these terms right here, and noteworthy is that we're going to have an R dot theta dot E theta and an R dot theta dot E theta. Oh, there's two of them. That's where that came from, right? And here is our R theta double dot. And right here is our centrifugal component right there. So that's where they all come from. One last thing that I said I was going to do that I didn't, and let's see if I can get this here. Remember I said that we had this component right here, right? That looked like that right there for path coordinates, and that was not tangent, that was the normal direction. My bad. And so how do we go about? Well, remember that this might as well be called R right here, right? That radius of curvature is the same thing as R, right? And so and if you wanted to, you could also say that the velocity, right? If the velocity in, let's say, in the R direction, right here, right, or the tangential direction, well, yeah, in the R direction, let's say. In the case of where we are, we're spinning about a fixed point, and we have a theta dot R right here is that V, right? I shouldn't draw that. Okay. That's theta dot times R right here. That velocity right here at the tip, right along here. If it's only along here, so that's going to be theta dot R, right? So if you square that, right, you could say AN is equal to theta dot squared R squared divided by R. Right here, right? You'll see that you have theta dot squared R. And there you go. So that's how they're related to each other. It's just mixing the things up. They're identical to each other, this portion and this guy right here. They're second cousins. Okay, so here's the example. We got that same race car, but now we have this radar unit that's spinning, and even though radar doesn't exactly work this way, this particular radar, yeah, I know, this particular radar has to spin and turn along with the thing it's tracking. Okay, but let's say that that's how it works. So it's being tracked by a radar unit positioned at the center of the track. The computer inside the thing, all it knows is the distance and the angle, right? Those are the things that it measures. So it uses variables of interest that are R dot, R double dot, theta dot, and theta double dot. All right. So given the location on the radar as shown here, determine the radial and angular transverse parameters, right? So this is going to be the same information we had in the previous example. So I don't think I worked through this. I haven't given you the values here, but I'll give you the values here in a second. Some of the other information that you needed to know. I think that's not supposed to be, I think that's just supposed to be like L right in there. Okay, so this is 250 yards, the length of the straightaway right there. So with that information here, yes, okay, so yeah, okay, so what we did here is that 375, by the way. That's 250 yards divided by 2 and multiplied by 3, right? So, because they're yards and we want to turn them into feet, and then we have the distance. So what we found here in this first thing, we want to get this distance R from the radar to the car when it's at point B. And we can also find the angle from horizontal right here, right? So we found that angle right there is what was said clockwise from horizontal. Oh, I guess it's going to be this angle right there is clockwise from horizontal, I believe. Yes, right? You think so? Yes, it should be. Yes. Okay. So we're able to find these important things. Yes. Okay. Yeah. It was clockwise. Yeah, it was clockwise. I'm sorry. Yes. Right in there. So that's the angle that we're using. Like I said before, I'd like to use counterclockwise. But it's saying it's clockwise. I guess this is clockwise right here. I think I should say counterclockwise. Okay. And before we can proceed, let's see. We need, with the other variables of interest, we need to put the acceleration into polar coordinates. Example 4.2, so that's the one that we did in the previous class, where we only looked at this portion of the thing. We did path coordinates. We found them in path coordinates, and then we transformed them into Cartesian. It's easier to use the Cartesian now, and then turn them into polar. But we could have done it from our path and gone straight to polar. We didn't have to go the intermediate route. So we generate a transformation matrix based on these coordinate axes, these coordinate unit vectors. And just want to see what time dinner is. Okay, and we generate the transformation matrix, and we use column direction to get the vectors right here, right? So, because we have i's, and we want to turn it into r's and thetas right here. So we set this up. And by the way, I didn't go into this in detail. You need to go back into the other class, in class 4, and work through this coordinate transformation matrix if you're not feeling comfortable with it, right? Or just look at it carefully and try to follow along. You have to do these yourself and try them out and figure them out to get them straight. Otherwise, they'll confuse you, especially like on an exam. So you need to practice the coordinate transformation. But anyway, we take this one in the I, and we turn it into r's and thetas. Take this in the j, and make sure we get the signs correct, and turn it into r's and thetas. And we do a similar, and so now we have the r, the vr, and the v theta a component right here. And then we do the same thing with the acceleration, right? Once again, using the coordinate transformation. And we have AR and A theta. Now we can get the variables of interest, right? Because if we write out, remember, I don't think I put it up on here. It would have been nice if I put it up here. Velocity is r dot ER plus r theta dot E theta, right? So this component right there is r dot. And now for the v theta part of it right here, right? You could just get, we know what r is. Now we could solve to get theta dot, right? So right here, so we get theta dot. Now here's the one that gets people get tripped up on, right? So we have r dot and we have theta dot. Now we go to the acceleration one, and the acceleration has just a little bit more effort. Because we know that AR is r double dot minus r theta dot squared, right? And we know that what the value is because we did the coordinate transformation. So we could just turn this equation around right here and say r double dot is AR, which we found from the coordinate transformation. We already know r, and we just found the theta dot when we were doing velocity. So we're able to get what r double dot is. And in a similar manner, we get the A theta, right? This is the expression for it, and we know what the magnitude of it is. So we already have r dot and theta dot, so we could rewrite the thing, and we could get theta double dot. And so just by putting in the values, right? And it turns out to be a really small number. So anyway, the variables of interest right here are all found. We got this from geometry, found this from the velocity, we got this from geometry, we found this from velocity, and then we were able to get the r double dot and the theta double dot. So we have all the variables of interest. So this would be the type of problem that's long and involved, especially if you were given the original problem that was in class 4, and then was asked to about this radar thing, you'd have to go through a lot of different steps. But the process of trying to solve it, the thought process in trying to solve it, is to try to organize your thoughts. Yes, I know. Organize your thoughts and organize what you know and try to step through and think it through. Right? And some experience helps in the solving, but like if it's a new problem that's got a new twist on it and you haven't experienced that twist before, what you have to do is try to stay organized and keep the big picture of what is actually taking place. So for more examples, please check out the books, the Engineering Dynamics Course Companion Part 1 and the Engineering Dynamics Course Companion Part 2. Right? They are published by Morgan and Claypool Publishers, and there are links down below to how to acquire them from the publisher. I think you can also find them on Amazon. Make sure you subscribe to this channel, and I will post some more videos. Feel free to include any comments, suggestions, corrections down in the comments section. I promise to read them. I don't know if I will reply to them in a timely manner, but I appreciate feedback. Thank you very much, and have a great day.